A lens is a transmissive optical device that focuses or disperses light by refraction. Lenses correct our vision through eyeglasses, enable us to view the smallest microorganisms and the minute chemical reactions through microscopes, and aid us in viewing the sky full of stars and heavenly bodies, including the moon through telescopes. How do we represent the effects of a lens on an incident optical field? We express it as a multiplicative phase transformation. Let's first consider a spherical thin lens, which is called so if the translation of light rays within it is negligible, or when a ray entering a point on one face exits at approximately the same x and y coordinates on the opposite face. It is therefore helpful to define the coordinate axis as shown. A beam of monochromatic light is incident from the left of the lens. The first face that it hits can be thought of as part of a sphere with radius r sub 1, while the opposite face can be thought of as part of a sphere with radius r sub 2. The lens optical axis runs across the optical center of the lens and along the z-axis. The index of refraction of the lens is n. The thickness function delta sub 0 represents the lens's thickness along the optical axis, while delta of x and y represents the off-axis lens thickness. Let the optical field incident immediately in front of the lens be u sub l of x and y, while the optical field across the plane immediately behind the lens be u prime sub l of x and y. Then, the spherical thin lens can be expressed as a phase transformation t sub l of x and y, and we can obtain the optical field u prime sub l by multiplying this to u sub l. In the paraxial approximation, we focus our attention to portions of the wavefront that lie near the lens optical axis. This greatly simplifies the phase transformation expression, especially after substituting f or the focal length of the lens into the simplified expression. The actual simulation setup looks like this. Positive input distance is to the left, and positive image distance is to the right of the lens. F is positive if it is on the same side as the outgoing light. First, we implement the Rayleigh-Sommerfeld propagation on the input optical field to obtain u sub l. Next, we obtain u prime sub l using the phase transformation t sub l. And lastly, we do another Rayleigh-Sommerfeld propagation, this time on u prime sub l to obtain the final image. The famous lens equation tells us that rays converge at S. Let's take a look at experiment and simulation results using a double convex lens with a focal length of positive 25 mm. At z0 equals 15 mm, the image is upright and enlarged, and enlarges further at 20 mm. This appears at the focal length, becomes inverted at 35 mm, then reduces at 45 mm but still larger than the input, reduces further at 55 mm but smaller than the input, and reduces even further at 65 mm. Here we fix the input distance and look at the light cone produced by the different image plane slices. The lens is located at z equals 0 mm. Indeed, the light rays get focused at the positive focal length. On the right is a different view of the image slices looking up to the location of the sharpest image at 50 mm. Another visualization of the image slices is shown using contour plots. You can also get the XY diagonal image slices cutting across the z-axis and examine better the image optical fields. If we plot a diagonal slice, this is what we'll see. If we plot more image slices, we can see the three-dimensional structure of the image optical field. Now let's look at the experiment and simulation results using a double concave lens with a focal length of negative 25 mm. Starting again at z0 equals 15 mm, we observe that as we move the input farther and farther away from the lens, the image produced becomes smaller and smaller, while maintaining its upright orientation. So far, qualitatively, experiment results agree with the simulations both for the convex and concave lenses. Here, we again fix the input distance and look at the light cone produced with different image plane slices. The lens is located at z equals 0 mm. The light rays are focused at the negative focal length. A different view of the image tries to show the divergence of the light rays towards the positive z-axis. Shown here are the RGB illumination simulations for both convex and concave lenses. For the convex lens, the formed color images seem to converge towards the other side of the screen, while they seem to diverge for the concave lens. Finally, let's look at the experiment and simulation results using a cylindrical lens with a focal length of positive 50 mm. Positive f means that the curved surface faces the input. We can extend the formulation of the phase transformation to the case of cylindrical lens as shown. Here, t sub l is a function of y only. For a change in orientation as shown on the right lens, the expression changes accordingly, and t sub l becomes a function of x only. For an input distance of 30 mm and a phase transformation t sub l of x, we see that the experiment result agrees well with the simulated one. For the other case, using a phase transformation t sub l of y for an input distance of 10 mm, simulation also agrees well with the experiment. Now let the initial orientation of the cylindrical lens be as shown. If you rotate the lens about the z-axis by theta, as measured from the x-axis, the expression for the phase transformation changes accordingly. For a lens tilted by negative 20 degrees about the z-axis, the resulting image instead becomes tilted by positive 20 degrees as shown. As we move the input farther away, the image stretches while maintaining its orientation. We observe the same behavior for a lens rotated by positive 20 degrees. The image is tilted by negative 20 degrees and gets stretched at a farther input distance. In summary, we've learned that the effect of lenses to the incident optical field can be represented as a multiplicative phase transformation. We've looked at the images formed by both convex and concave lenses using various visualizations. And lastly, we saw what the images look like using RGB illumination and for cylindrical lenses oriented differently and tilted about an axis. Thank you for watching.